Okay, so we're going to move on. We've been talking about those fractional designs, which are really kind of combinatorial puzzles in a sense, but we're going to move on to a more mathematical approach or continuous scale approach. First, quote from Gilbert and Sullivan. Gary helps us set the stage. I am very well acquainted too with matters mathematical. I understand equations, both simple and quadrilateral. About binomial theorem, I'm teeming with lot o' news, with many cheerful facts about the square of the hypotenuse. So, Pirates of Penzance moment. So response surface methods are really good when you have continuous factors in your model and your goal is finding a point of optimization. So when I am in person in front of a class, when I start teaching, pick up a piece of paper that we don't need or a student doesn't need, I'll crumble it up into a ball and then I'll pull it back out, and it's a mess, of course. But you have a surface, and the surface is very irregular. It doesn't have a normal shape, but you can find points, high points, and you can find low points, and that really gives you the idea of what we're doing with response surfaces. We have these continuous scale domains, so the x and the y that make up, the length and the width of the paper. We can find a point at which the x and y maximize that response, z, of the function. We also might want to describe that surface in some quantitative way. Okay, this is really used, just like the fractional designs, these are used a lot within industry and engineering. I know, having talked to some people in data science professions, some of the major companies are looking for people who are response surface methodologists because most people with data science training don't have that expertise, and it's actually a very important area to understand for working in industry settings when you are working on a team that is working on applied problems. Let's get to the next slide here. Okay. So here's an example for just providing a little concrete context. We want to know how the arm length, the rope length, and the mass of a counterweight affect the throw distance of I don't know how you say that. Trebuchet is all I can think. It's French, but it's those. There was a picture in the old set of notes, I forgot. It's those machines that have a weighted object, a counterweight at the end of the string, and then it throws an object, okay? We have the three factors that can be varied. These are all continuous. The arm length is continuous, the length of the rope, and then the mass. And a function could give the average of your throw distance for the parameter settings. So you could have any arm length, any rope length, and any mass counterweight, and give the length that the trebuchet is able to throw the object. So here's another example. A Harvey Wallbanger is a cocktail made from vodka, orange juice, and Galliano. We want to know how the amounts add up to get the best taste. So the perfect proportion is really what you want to make the best Harvey Wallbanger. The gotcha, the reason why Gary calls this a gotcha example is because the proportions matter, not the amounts. So it's all about that relative proportion of vodka, orange juice, and Galliano. Here it's a mixture design rather than a response surface. Even though we're really kind of talking about the same thing. It's just that there's a truncation on the mixture. Okay, so the famous quote attributed to George Box is, "All models are wrong and some are useful." We don't expect any of those models we use in a response surface to be exactly right. They're not describing reality. They're describing what we observed in the data. And most of the time, if we do it correctly, the model is good enough to help us understand what we need to understand and meet our goals. So don't get too excited about how simplistic the models can be, but just use them. Even if you think, oh, that's silly to do it this way, we could have something far more complex, don't give in to that. That doesn't help you at all. Just keep it simple, stupid, as the saying goes. Okay, here's the general form of a response surface. This is really just a very general nonlinear equation. We have continuous factors, x1 up to xq, and an error. And then it's predicting a y. What is the shape of f? Where is f optimized? Where might we use a constraint optimum? And what direction do I move and from where to improve the response? These are all things we might want to understand about f. Here's a very simple first order model. This is just a multivariable, regression model. It's just a first order multiple regression in particular. The second order model would be to add these quadratic terms and the cross product terms, the interactions as we typically call them in a regression class. Very simple. Often, even though these are super simple, they're good enough as long as the function is reasonably smooth and we are looking for sufficiency locally. Sometimes getting that global sufficiency is really difficult. Here's an interesting function as an example. Notice we have our two continuous scale predictor variables, x1, x2, and our response that we're modeling. We can see kind of like a ultimate optimization point here. If we look at a contour plot, we see that the contour plot does not really reconcile with that 3D plot. Okay, notice how our optimum point is over here at x2 equals 0, x1 approximately 7 or so. Whoop, I keep switching back. Let's try that again. Okay. It's difficult to see how that reconciles with the contour plot. For large values of x2, the first order model might be adequate, but for those smaller values of x2, particularly that point where it's butting up against 0, there needs to be a second order model. And you can see that because of that inflection point. And it's going to be tricky to model this because it's only going to be correct even over a very small range of x1, as we could have seen from that first point. That contour plot I would have found very misleading if I had not seen the 3D. So there are other ways we can write this first order model. First order models can be a tilted plane in general. That's how you want to think of them. And the contours are the lines of that tilted plane that go along. I can't show you this because it's virtual. And beta gives you a direction of your steepest descent. So if you want to increase your function quickly, you move in the direction of beta. That is, you go by some multiple of beta for adding to x. Here's another way you could write a second order. Notice that again, this just really combines the terms into these sums, but it gives you a sense about how you can think of this, how this is the linear portion, and this is the quadratic portion of your second order model. So once again, we've got a matrix that describes our parameters of the model. The diagonal of that script B, this guy right here, is the pure quadratic coefficients. and the off-diagonal elements are those cross products coefficients. So this is a very easy to understand idea that you just look off diagonal to find those cross products or these interaction terms, and on the diagonal to find the quadratic coefficients. We only have the KL cross product, and that's because for K less than L, and that's because we have symmetry. So we really don't need to always include K. We don't need, it would be redundant to include both KL and LK. So we can actually divide the number of those cross product coefficients in half. The second order models are remarkably good at describing a wide variety of spaces, such as this. Notice we have a minimum. If you kind of imagine you could see down into that quadratic kind of plane, there would be a minimum point. You can see the minimum down here. I would like to be able to see down into it too. But here's a maximum, where again, if we could look up, that point on the other side would give us our maximum. This would be called a ridge, because it gives us a point of inflection across a wide variety of points for x2. And this is a saddle, okay? Sometimes these saddles are difficult to approximate in practice, but you can see why it's called a saddle. It looks an awful lot like a saddle, but we see that inflection point going along these values, in this case of x1, but we reach a point of an optimum point, a maximum in a certain region. Okay, so the shapes are completely determined by the actual values of that regression vector, or matrix, I should say. And we just need to determine the point x0 and a matrix H, which is called the hat matrix, to make our canonical variables, V. Okay? The function of the canonical variables is then written right here, and it's going to be just the point at which we reach this kind of base, okay, plus these quadratic points based upon these lambda steps. So notice that here, that base point is going to be the point at which f of x0 is equal to the point of f of x0. Said that wrong. So if the lambda i's are positive, then we are describing a minimum. Okay, why is that? Oh, I don't know how my slides keep changing. There we go. Because we're increasing from that base. Okay, if all the lambda i's are positive. If they are negative, then the shape has a maximum, and that's because we're decreasing from that base. Or all of them are of one side, or if more of them is close to 0, then we're going to get something like a ridge. Okay, that's describing that point where it's kind of like a constant term across one of the domains, x1 or x2. If some are positive and some are negative, then you get a saddle. That's why I often think these saddles are more difficult to describe sufficiently. It's more complicated than just a surface where you get a minimum, or a surface where you get a maximum, or a surface where you describe a ridge in the data. Those saddle points are difficult to describe sometimes. Okay, so the matrix H contains those eigenvectors of beta, and the lambdas are the eigenvalues. So you can do a simple eigen decomposition of your matrix beta and get back the points H and lambda. Note that this is consistent with a least squares model, of course, that we can retrieve x0 our point that makes that basis by taking the basically information matrix associated